29. And the first thing I'm going to do is I will go over what is really called the problem solving strategy for Faraday's law. The first thing is that we need to know that Faraday's law relates the induced EMF to the rate of the change in the magnetic flux. The magnetic flux is I will say, it has to do with phi times the area cosine the angle, and based on how much we're going to have change or in what direction this change is, the EMF is going to be. Now, I will say to calculate this rate of change, you first have to understand what is making the flux change. Is it the conductor moving towards or moving away? Is it there is a switch making it on and off? There is a change in the area. Then all the time you need to know what is really going on with how really the flux is changing. Also, one of the most important things is you need to pay attention to the direction of the vector A. Vector A, or the element dA, is actually the area vector. It is always perpendicular to the plane of the area. And here we have two choices. If we have the area in the horizontal plane, you could point up or down, and you are going to choose one direction for the area that is going to stay the same for the whole problem. When we want to calculate the flux, this is the equation 29.2, which is phi b equals b dot a, which is ba cosine phi. And when b is uniform, we can, of course, have that equation valid. And when we have b non-uniform, then we're going to have integration of b times dA cosine phi. According to Faraday's law, the induced EMF, this is 29.3, EMF equals negative delta phi b over delta t, or if the conductor has so many turns, then we're going to, of course, have that n in the equation. We are going to apply the sine rule described before, like we did describe it. This is the one that we described here to find, these are the examples here that I did go over, and this is the explanation for the sine. You need to apply the sine rule for you to determine what is really the EMF. Now, one of the most important, actually, applications of the induced EMF, it is the generator. And when we talk about the generator is simply just a coil that is turning in a magnetic field. Then there is a magnetic field that is, this coil is immersed in, and that we're gonna start rotating that coil, and based on that we are going to see, look here, this is really the loop seen and on, like we're gonna look at it and see, like here it is perpendicular, here it has an angle, then it rotates, it keep rotating, and based on that we are really here plotting what is the flux and also what is really the EMF. And you can see that the EMF is gonna follow sinusoidal dependence, and I will say this is really the equation theta b equals AB cosine phi, and from that we can say BA cosine omega t, and then the EMF is gonna be the negative, the change in the I would say flux over time. Then it is W omega times B times A sine omega t. This is what is going to be the EMF that is resulting. I will try to have that video 29 too. Okay, just demonstrate.
In example 29.2, we're going to calculate the magnitude and direction of the induced EMF in a 500-loop circular coil of wire that's in a changing magnetic field. Specifically, we have a coil of wire sitting between the poles of a powerful magnet. The magnetic field going from the north pole to the south pole is uniform and is decreasing at a rate of 0.2 Tesla per second. The coil is oriented such that the plane of the coil makes an angle of 60 degrees with respect to the applied field, so that's the angle here. And the coil has a radius of 4 centimeters, and we want to calculate the total EMF induced in the coil. We're going to use Faraday's law of induction for this problem as given here, where N is the number of loops in the coil, which in this case, of course, is 500. So the flux is simply the magnetic field times the area of the coil times cosine phi, where phi is defined as the angle between the area vector of the coil and the applied field. So that is in fact 30 degrees and not 60 degrees. The field is the only time-dependent variable in the problem, and so d phi dt is simply dB dt times A times cosine phi. So I can calculate the area from the radius, and I have N, and I have dB dt, which is minus 0.2 Tesla per second. In fact, I need a minus sign out in front. These two minus signs cancel, and I get 0.435 volts. So if I look at the coil from the left, in other words, I look at it from this direction and place my thumb in the direction of the area vector, then my fingers will naturally curl in the direction of positive current flow. I have a positive voltage, so I need a positive current flowing, and that will in fact be clockwise. If in fact the magnetic field were not decreasing, but were increasing at 0.2 Tesla per second, then this minus sign right here would not be there. It would be a positive sign, and I'd have the minus sign in front, and I would have gotten the opposite sense of voltage, and of course the current then would be flowing counterclockwise. And this ends example 29.2.
All right, this was as an application to the Faraday's law, and also related together we are using, I will say, Faraday's law together with Lenz's law. And for Lenz's law, we are going to do so many applications, and it is actually a convenient method for determining the direction of an induced current or EMF, and always is telling you that the direction of any magnetic induction effect is such as to oppose the cause of the effect. And I will say this is a natural, this is something done by nature. Nature doesn't like things to you go up for like no a limit. It doesn't like it to decay, and therefore it likes to have always kind of something in the middle. Then if like here when we apply this to the magnetic induction, if the original field is gonna have the trend of like increasing the flux, then there should be something to stop that continuous increase, and then we're gonna have a change that is gonna oppose it, and therefore we're gonna have what is called the induced magnetic field is gonna be in the opposite of the original, and if there is a decrease we wanna support it, then the B induced, it should be in the direction of the B original. Here, for example, in the figure, there is a uniform magnetic field and the magnitude of the field is increasing. Then there is an induced EMF driving a current as shown, and based on that, we are going to find that the B, if you look at this is the original, it is increasing. The induced, it should be in the opposite direction. We can here show some examples of Lenz's law. For example, of course, like you're gonna have different examples. Maybe moving a magnet towards the coil, or having a switch on and off, or changes in area that is gonna cause the change in the flux. Motion of the magnet causes increase in downward flux through the loop, and then my B induced is going to be in the opposite of the the original. Like here, I will say the original is going this way. Like if you look at it, based on the magnetic field, it's like north, the direction of the north, and then B induced is going to be up. Now here, the magnet is causing decreasing upward flux through the loop, because here, if we look, we have B original is up, and then B induced is going to be in the same direction because there is a decrease. Here we have the north is moving away, and it's the same idea. Now here we have what is called motional electromotive force. We have here just a conducting rod, AB, that is moving perpendicular to a uniform magnetic field, and because when we move it, we're going to create an EMF. We call it motional EMF, and it is an induced. And the value of this EMF is going to be V times B times L. V is the velocity or the speed, B is the magnetic field, and L is the length of the conductor. Now, I would say the general form of it, with any shape, moving in any magnetic field, uniform or not, is going to be DEMF is going to be V cross B dot DL, and that is, the equation that we are going to use and integrate for any closed conducting loop. The total EMF, it is really, having that equation, the closed integration of V cross B times DL, and this is how we're going to calculate the EMF. I want to introduce also the 29.7 example here.
In conceptual example 29.7, we're going to consider Lenz's law in the context of the slide wire generator that we considered in the previous two examples. The generator consists of a U-shaped conductor sitting in a uniform magnetic field, which in this case points into the page. The circuit is completed by placing a rod over the legs of the conductor, and we're going to apply a force to this rod and move it to the right at a constant speed, V. Now, as is clear in the diagram, the area of the circuit grows with time, and hence the total magnetic flux flowing into the page grows with time. Conducting circuits, however, don't care about what flux they have, they just don't want it to change. So in response to this increasing flux into the page, the circuit induces its own current, I, which flows in a counterclockwise direction. This is going to produce a magnetic field, though albeit maybe a small magnetic field, but it's going to produce a magnetic field that's actually out of the page. The effect of this magnetic field is to counteract some of the increasing flux into the page, And this is the basis of Lenz's law, and it's the argument that's used to determine the direction of the induced EMF and the direction of the current flow. And this ends conceptual example 29.7.
All right, then this is the example here, conceptual about what we have for, Lenz's law. I will stop here and post another video.